I'm live. Hey, excellent. Yeah, that bright backdrop is a problem. But I'm going to be rearranging my room and my space real soon. So. We're just getting everything launched. We're ready to go. I forgot to update the website last night. So I did a night stream last night. So Tuesdays are night streams, 9:30, 9 to 10:30. Very chill. I like doing math stuff kind of later. It's a nice just nighttime activity for me. So I'm hoping that those night streams actually are popular. I'm gonna get the website all updated with the correct stream. There we go. And then I'm gonna, here, let me share. There we are. So go to thecalculustutor.com to submit your questions. While you all are doing that, I'm going to step away for just a second, go grab some coffee, and I will be back in just a moment, and we'll get ourselves started. So yeah, go to thecalculustutor.com, submit your questions. I'll be back in just a moment, walk you through the question submission process in case you're getting stuck somewhere along in there. There we go. Excellent. Okay. See y'all in a minute. Go to thecalculustutor.com, submit your math questions. 1 second here. I'm going to try to adjust these blinds a little bit differently. Oh, okay. There we go. Okay. Well, the far ones, I was able to close a little bit more tightly. Whew. I feel blind now. Huh? How does that do? Not great. And there's like this. Something worse? Better? Neither really. Me over there. Oh, it's over here. Yeah, there's just bright spots. It's bright outside and it's just shining around the blinds. So, okay. But that is a problem for today's stream, but it's not a problem that will persist into terribly many future streams. Oh, there we go. There we go. So yeah, glasses on. So if you navigate to thecalculustutor.com because you have a math question you'd like to submit, this is what you'll see. So the stream is just is contained here. You can watch it just on through the YouTube page as well, and that will look familiar to you if you watch any amount of YouTube. And you know, there's the rest. There's about me. This is for people who want to inquire about one-on-one tutoring, information about that, reviews, all that sort of stuff. But what you want is this submit a question. I know, and it'll scroll right to that section of the dedicated streaming page. And you can submit questions 2 ways right now. You can use the submission form, which is just a Google form, or you can email me directly. And here are some guidelines for if you email me directly. But I want the form hopefully to be the best and primary way. So if you click, there we go. Now, if you don't, one thing you might see instead of this is a Google sign-in page. You have to sign in to access this form because you can submit pictures. And anytime you submit files, Google requires that you are signed in. So sign in with your Google account. Go ahead and try to sign in. Try to use your school Google account if you have one. Because if you do sign in with your school Google account to try to access this, it might then say, oh, you can't. If it says that, you should tell me that. Submit your question via email instead, and in that email, tell me, oh, I'm from such and such school district. I couldn't access your form. And I think I can just reach out to the districts themselves and have them make this form accessible. Maybe, I don't know, fingers crossed. But suffice it to say, if you realize you can't access this form, please let me know. You should be able to access it if you have just a personal, like non-school Google account. You should be able to just use that. So that said, here's the form. You have to check this and say, yes, this is my email address, but tell me who you are. It doesn't have to be your real name. Just whatever when I'm answering your question, say, oh, this question was submitted by such and such. So tell me how you'd like me to refer to you so you can know when I'm answering your question. Tell me your pronouns if you care. That way, because in addition to your name, I will likely need to use more generic pronouns to refer to you as I'm answering your question. And if you don't tell me, I will probably just use they. Where did this question come from? The teacher in class, right? Mr. Smith's 6th period algebra. Actually, you don't even have to tell me the period. Just Mr. Smith's algebra. That's plenty. So teacher in class. If it didn't come from a class, then just a very brief description of like how you came upon where this question is arising in your life. This is mostly to help me organize these and to help other students find them. Okay, then the meat and potatoes here. Ask your question. Be as specific as possible. You can type like more or less as much as you want into this box, but you don't need to type a bunch. So what I've been saying is don't just type in, number 8, and then down here send me a picture of your entire textbook page of math problems, or your entire worksheet of math problems, or whatever. Yes, tell me number 8. But then be specific about, so yeah, send me the picture of your worksheet with the problem, or the picture of your textbook page with the problem. And tell me which number you want help with. But then tell me, what about number 8? Like I did A and B just fine, but part C asks wants a graph, and I don't know how to graph this kind of equation, right? Something like that. One sentence. Granted, it's kind of a compound sentence, but you could, want to graph. I don't know how to graph this kind of equation. Boom, that's enough for me. But maybe you didn't get A and B, right? On one of these multi-part questions. Maybe you look at number 8 and you're not even sure what it's asking you to do. You could say that. You're like, I'm not sure what this question is asking me to do. You could just say that. Like, that is specific. That lets me know from the get-go the instructions and the setup for the question are causing you some confusion, or for whatever. That's the first place you struggle, and I can spend some time there. But if you don't tell me you're struggling to get started, I may not spend as much time on the getting started part, right? So this is you directing me about how to best help you with that problem. So anyway, be as specific as possible. 1 or maybe 2 sentences is all you need, though, when I say be specific. You could just, we didn't do this type of problem in class. That's specific. That just tells me you have this problem, but you're not sure what to do. Okay, and then we'll skip this for a second. The other meat and potatoes, images. Attach an image of the math problem, whether it's so like take a picture with your phone or whatever. Yeah, and so the goal here is to be clear and complete. Take a picture of the entire problem so I can see the whole problem, so don't crop any of it out, and make sure it's not blurry. And if the text is small, make sure when you zoom in that it's legible. Now, I don't know, this might compress the pictures like crazy, and so you might do your best and it still might end up blurry on my end. I'll have to deal with that as part of this process. But from what I can tell, this should work pretty well. But that said, it might be better to take a picture of the specific problem rather than the whole textbook page. So the other part of being complete, though, means, yes, take a picture of the entire problem, all parts, even if you're only asking about part B. Try to include all the parts, even if it goes down to part J or whatever, because those other parts will help me understand what the question is trying to get you to learn. Because remember, all these problems are ostensibly about teaching you math. So anyway, make sure you capture the whole problem, but also oftentimes there's a separate block of like instructions, like in bold or whatever, for a group of problems, right? Your textbook, has the block of instructions, some problems, and maybe the problems go into the next column. Your worksheet has instructions at the top, or instructions at the top of each section. So if those instructions aren't included with your initial picture of the problem, also include an additional picture of those. Any diagrams that go with the problem or graphs, right? Include, and my goal, I'm not trying to make this tedious. My hope is that you can just, and then the other thing you might include is a picture of your own work. My promise to you is that your work won't show up on the stream. unless you check this box. So if we go back up here, but this box starts off unchecked. I assume most people don't want me to show their work, but it can help me answer your question better and understand, because the goal here isn't just to give you the type of answer that the AI that ChatGPT could give you, that it isn't to give you a generic answer. It's to answer your specific question. That's what I'm trying to offer here. I'm trying to essentially offer what I offer to the students I tutor one-on-one, but I have a lot of students that just have like a few questions every now and then. They don't need to meet weekly at the same time every week or multiple times a week. They need to meet like once every 2.5 weeks to have their 5 questions answered. And a lot of times they've saved up those questions until they have enough that they feel like it's worth meeting. My hope with this is, instead of having to wait until you can schedule a formal session, you can just pop in when that one question comes up on that homework assignment. You can pop into the stream and have that question answered when you have it. And that is actually going to help you learn way more. Just there's something about the urgency of it. Anyway, so attach clear and complete images. Please include a picture of your work, but you don't have to. If you're okay with me showing your work on stream, go ahead and check this box, but I expect that most people will not check that box, and that's totally fine. In fact, my assumption is always going to be that people haven't checked it, and if for some reason, sorry, there's a little gnat floating around. If for some reason I'm like, oh, I'd really like to show this on stream, I will then go and check and see if the person checked the box. But most of the time I'm going to assume that people did not, or I'm always going to assume that. So if you can't access the form, so you go back to the website and you're here, you can email, and you just click right here on the website and it should open your email. And here are those guidelines, same thing as the form asked, 1, 2, 3, 4, right? Just how you want me to refer to you, what name you want me to use, and pronouns if you care, problem source, teacher and class, your specific question, 1 or 2 sentences, and your clear and complete pictures. And yeah, that's it. And then if you're like, yeah, sure, show my work on stream if you want to, go ahead and include that. But like any submissions that come in through email, if they include your work, you are automatically opted out of having your work shown on stream. So I'm trying to emphasize that a lot. Maybe people aren't worried about that. My assumption, having worked with students in class and stuff like that, and seeing a lot of the nervousness and trepidation about going up to the front of the class and showing work, and even sharing your work with your elbow partner or whatever, has told me that students are really anxious about having their work that they did for just their homework shown to other people. And so I want to respect that, and I understand it. But I actually added that checkbox somewhat recently, because it did occur to me that there might be some people out there, especially teachers. So my hope is that I will get at least some traffic from teachers, because I haven't talked about this a ton on any of the previous streams yet, but like, this could also be a resource for math teachers. Your math problem is, how would you teach this concept? What's important about this concept? Just as a way to like bounce an idea off. Or if you're also a tutor out there, like, this is free, right? That's the whole goal. It is free. And the goal is not just to answer homework questions, but to answer math questions. Because my favorite thing about math, my two favorite things about math. One is teaching math, the process of helping somebody go from not understanding a math concept to not just to understanding that concept, but to understanding the usefulness of it and understanding the value of understanding it. But so that's one thing I really like. But my other thing that I love about math is using it to do stuff, right? Knowing that I understand a system or a process enough to bring my mathematical knowledge to bear on it. And it can happen all over the place. I feel like I'm better at video games than my skill would otherwise allow me to be in some cases for some games, because I understand mathematically how either some underlying systems of the game work or just how math has to work. I talked about this. I don't think I talked about this last night. I think I talked about this on Monday, but I talked about Balatro, and I think of Balatro is just math the game, but there's a lot of like just probability in that. Like that's because I understand probability, but also some other things. Like, this is not going to make sense to anybody other than somebody who has played enough Balatro to not only have unlocked the plasma deck, but to have played with it at all. But anyway, the plasma deck takes your chips, your chip number, your blue number, and your multiplier, your red number. And before it multiplies them together, it equalizes them, right? It adds them together and then splits them evenly. And that's, that's kind of a weird thing to do. Why does it do that? Because for any total, the biggest product you can get is to split that total in half and multiply it. It always is. That's just mathematically true. It's so like for any given length of fence, if you want to enclose a rectangular area, you'll be able to enclose the most area if you make that fence square. The true most area to enclose with the least amount of fence is a circle, but that's not really applicable to my Balatro example. But anyway, it's the same idea. An area is a length times a width, so you want to maximize the result of that length times the width. Well, if you know the length and the width have to add up to a certain number, which you would if you know how much fence you have to use, or in the case of Balatro, the chips are like the length and the multiplier is like the width, you know that number will be the biggest for any given total of length and width if the length and width are the same. So, for example, if you have two numbers that add up to 10, if you want them to multiply to be the biggest possible, what two numbers that add up to 10 have the largest pot? Okay, let's do it. Let's go to we just stumbled our way into a math conversation. This is fantastic. This is what I want to have happen. Reminder really quick while I'm transitioning into the Miro board. There's no stream tomorrow. I have jury duty. I talked about it last night. It's just jury duty is just such a random weird interruption for everybody. Like, it's not, not for me in particular, just literally, and there's kind of no way around it being that for people. So I think we have to have a good humor about it and not see it as a burden. It is a disruption. But in order to have a trial by jury, we have to have people to be jurors, and we can't just let the volunteers do it, because that's a self-selected group. You have to also have people who don't want to do it, people who are highly inconvenienced, people who are too eager to do it. You have to have all the types. You guys. Oh wait, it's because I'm so sorry. Okay. Give me a second. I signed into the wrong profile on my tablet. So we're going to get in here. We're going to talk about this square rule. But yeah, so I'll be doing jury duty tomorrow. Civically, potentially passing judgment on people by trying to understand and apply the democratically decided and enacted. It's pretty cool. And there's a lot going on right now that makes every part of that sentence feel worrisome. But we do still have it. I will still happily do it. But also it's an opportunity for, my particular values to be reflected in the system, right? We have to look at the laws and things like that, but like I get to, if I have to be, if I end up getting chosen to be a juror and I have to cast a guilty or innocent verdict, a black and white thing, that decision will have to come from the way my values intersect, the particular evidence and particular applicable laws and things like that. So I don't know. It's just, I can't, as much as it is like a disruption, right? I can't bring myself to complain about it, because I would rather have that disruption than not have it, right? And I think we all feel that way. Well, I can't say I think we all feel that way, but I hope the vast, vast, vast majority of us feel that way. All right, so here's what we're doing. I'm going to set, I want to show cursors. There we go. I'm going to bring everyone to me. Okay. So what we're talking about here, for two numbers oh my gosh, I'm going to try to write legibly. Whose sum is, we're just going to say 10 for simplicity, right? What is the maximum product? That's a P. Product. There we go. Okay. So two numbers whose sum is 10. Well, we can call those X. Sum means plus Y equals 10. And we want to know the max of X times Y. Well, I mean, one way to do this is just to start investigating, right? And in fact, I think that's one of the best places to start for something like this, right? So one way to investigate that occurs to me, let's make a table. I like using this tablet. One, because it's just so freeform and it just is so fast to do stuff, even though it's imperfect. And I think there's a lesson in that, especially for me. But also because it emphasizes something that's really important to me, which is math is done on paper and is messy. Math isn't. Not every aspect of interacting with math is perfect, right? And yeah, and like to learn math, you have to do it. You have to get on the paper. So anyway, so here's what we're going to do. We're going to do x, y, and then we'll do x times y. And we can do 1 and 2. So let's see what happens sort of at the low end there. And we could literally just do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, if we did 10, we'd have to do 0, and 0 times anything is 0. So it's probably not anything that has to do with 0. So we'll start at 1 and 2. But let's also look at, we'll skip 3 and 4, and we'll do 5 and 6. And then we'll do 8 and 9. Right, so if they have to add up to 10, if x is 1, then y has to be 9. Let me put that over there, 9. If x is 2, to add up to 10, 8 would have to, or y would have to be 8. If x is 5, then 5 plus 5, 6 plus 4. Oh, actually, let me go ahead and put a 4 here. There we go. Now we're just sort of skipping one number on another. You know what? Why even skip a number if I'm only skipping one number on each side? So let's just do this whole thing. 3 would pair up with 7, 6 with 4, 5 and 5, 6 and 4, 7 and 3, 8 and 2, 9 and 1. So we end up having these repeats, right? And when we go to multiply them together, because the order of division or multiplication doesn't matter, we'll end up with sort of this symmetrical looking thing. But let's investigate. So 1 times 9 is 9, 2 times 8 is 16, 3 times 7 is 21, 4 times 6 is 24, 5 times 5 is 25, 6 times 4 is 24, 7 times 3 is 21, 8 times 2 is 16, 9 times 1 is 9. And so you can see 9, then we jump, we almost double from 9 up to 16. Then we increase, but not nearly as much, up to 21. And again, not nearly as much, up to 24. And then just a little bit more up to 25. But then back to 24. And we could say, oh, well, is there a number slightly smaller than 5 and therefore slightly bigger than 5 that would give us a multiplier bigger than 25? I mean, that's a question that occurs to me. And so what I want to model here is listening to those questions that occur to you, right? I was like, that was the first question that occurred to me as I saw this pattern. And so I'm trying to model following that investigation, right? What would, so what about like 5.1 times 4.9, which is the same as 4.9 times 5.1, right? What is that? Well, let me do my calculator real quick. 5.1 times 4.9. That is 24.99. Exactly, by the way. I did not round that. That's 24.99. We went just a little off from 5. Remember, they have to add up to 10, right? They have to add up to 10. We went a little off from 5, and we got a little off from 25. There is our max right there. is 25. And notice it's when they are both 5s, right? And so it doesn't matter that the total here was 10, right? It doesn't matter what the total is. You're always going to end up with this phenomenon, right? Where the lowest value of one variable is going to correspond to the highest value of the other one. And as you look at the products are always going to get bigger as you get closer to the middle of this list, no matter how long the list is, and it will always maximize where they're equal to each other. Now, granted, you can make all sorts of changes to the setup. So, like I mentioned, like a fence, right? If you have 100 feet of fence, and you want your whatever enclosure to be a rectangle of some variety, how big should the sides be? So let's ask that. With 100 feet of fence, what dimensions give the largest area for a rectangular enclosure? Right. Okay. So that's our question now. So this is related, right? And let's talk about how this is related. Maybe you don't see how this is related. So we want a rectangular enclosure. So it's going to have some length and it's going to have some width, right? And we're assuming that, we're going to use all 100 feet, and that there will be no like waste at the corners or connecting bits, and we're not going to worry about a gate or anything like that, right? We're dealing with what would be referred to as the mathematically ideal version of this, and that's not to say we couldn't address those other things. The value of a mathematical ideal is that it's a starting place, and it allows you to get a handle on the core sort of foundational systems of whatever you're looking at. And then from there, you can start layering on complications, and complicating factors and things like that. So there is value. I think this is a place where like mathematicians get criticized, especially by people like physicists and engineers and things like that. With this, mathematicians always playing in these idealized worlds, right? And yeah, while these idealized worlds are not perfectly analogous to the real world, they are the basis from which we can understand the real world. And there's all sorts of things that are fraught about that approach, right? I'm not saying it is the only approach we should use or even the best approach we should use. I am saying there is some amount of value to it for problem-solving purposes such as this. So in this idealized situation where there's not going to be any waste, and all 100 feet can go to either the length or the width along either of the sides. So we know that 100 feet of fence has to be equal to this length here plus this width, but also plus this length down here, also plus this width over here. So we end up with, if I just reduce it down to the numbers, there's 2 L's and there's 2 W's. I'm going to factor out that 2. And there we go. This situation, the perimeter results in this relationship between L and W, which shows us we want to add 2 numbers together. We want to find the sum of 2 numbers such that they, when doubled, they add up to 100. Well, we could divide out that 2 if we wanted to, right? We just divide by 2, and we can call this 50 equals L plus W, which sort of makes sense. If the whole fence is going to be 100 feet, then just one length and one width will be 50 feet. And if you maximize the area associated with that, it's the same area, right? And here we have it. L plus W, instead of equaling 10, now they equal 50. But the process is going to be exactly the same. 1 in 49, 2 in 48, 3 in 47, blah, 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 it all the way down until you get to 25 times 25. And so, yeah, so what values of L and W give us the largest area? So this is what's referred to as an optimization problem. I guess I'll just mention that. All of this is oops. You still following me? You are still following me. Excellent. Okay. All of this is actually these are optimization problems is what we're talking about here. This is just one form of optimization, but so essentially what we have here, now that we're really talking about something real, but at least like we can understand the idea of enclosing a field with fence, right? Like that's a thing that people actually do. So what we have here is we can for this optimization problem, we are trying to optimize. So our goal is optimize the enclosed area, which is just the product L times W given the constraint of 100 feet of fence, which is that 2W plus 2L equals 100, right? That's that equation. So our problem here, what we are trying to do is we're trying to optimize the enclosed area. What's the optimal amount of area you can enclose? In our case, we're going to say it's the maximum area. Now, granted, there are other conditions for optimization, and so we do want to define what does it mean to optimize this, but in our case, we're trying to find that maximum area. And there's so many ways to do this. We did it with a small number, right? By just looking at the list, and we can just see it. And we can do that with whatever numbers we want, right? And we even showed. Sorry, I'm bouncing around a lot here. I'm going to try to do this more slowly. Hopefully that makes it less jarring on the stream. We even showed that, like, okay, that's true for these whole numbers, but is there some more optimal place? And we showed that even when you go just a little bit off of that optimal spot, your product diminishes a tiny amount. But if you're really trying to maximize, do you want 25 or do you want 24.99? Maybe 24.99 is good enough for you, and there's a reason that you want one dimension to be 5.1 and the other one to be 4.9, in which case this would actually be your optimal result because this is within your tolerance and this fits some other criteria or constraint, right? So optimization problems always have a constraint. Sometimes the constraint is unstated. Sometimes the constraint is just the so I guess there isn't always a constraint problem. Like if you're trying to like optimize the flight path or like the height something reaches, No, your constraint is the strength at which you can launch it or something such. So yeah, optimization problems, at least in real life, always have constraints. Simple optimization problems have a single constraint, but more complicated and realistic problems, optimization problems, have multiple constraints. And then you get to the real world, in which case you're trying to optimize 3 different things given 100 different constraints total, that type of thing. So we talked about a list. Let's talk about another way to talk about this. I'm going to open a Desmos tab. I'm not going to show the Desmos just so I don't have to flip back and forth between shared screens. But I'm going to, once I have the graph up, I'll just copy paste it into the Miro board. And that I think will be faster. Oh, no. Okay. So I have this. Now I just need to scale it. I mean, actually, it could be useful to... Yes. So I'm in Desmos. Hopefully you all are somewhat familiar with Desmos. And if not, Desmos.com, best graphing calculator I've ever used. Totally free. It's amazing. All right. So can I get rid of that and it's fine? Okay. I can't. Can I undo? I can. Okay. So ignore this L equals X thing. That's letting Desmos know. When I say L, I just mean X. So here is our L plus W equals 50 equation. I've rewritten it so that it's W equals because it seems like Desmos likes that better. But that suffice it to say, the width, if we know what the length is, then we can figure out the width by just subtracting the length from that 50, right? And so this is that L plus W equals 50. And then L times W, that's the thing we're trying to maximize to get the most of, right? We want the most area. And so when I graph these, we get this graph initially. So I want to clean this up really quick. You can see I have 2 green lines here and they're sort of going together. It's a parabola if you've encountered quadratics or parabolas in algebra yet. So what I want to do here is I'm going to go to the settings and my x-axis. I want to have, it goes through 0, 0 here, but I want to have a little room to the left. So I'm going to go -5. And then it also goes to 50 here, but I want to have a little room to the right. So I'm going to go up to 55. And there we go. You can see it spread all the way across. Now, y-axis, you can see negatives. It goes down below the x-axis pretty far. And we don't actually need the negative y values. They don't mean anything for us here. And we'll talk about that in just a second. So I'm just going to have that go down to -10, I think, because the scale of my y is going to be bigger than the scale of my x. So the green, we can see it going up here and sort of coming to the right. And over here, what it's doing is there's a hump up top there. It goes up and over. So we want to see that. So it goes up to 185 right now. It looks like it needs to go up quite a bit more. So I'm going to take it all the way up to 500. Okay, I thought that was really a big jump. So I'm actually going to go up to 1,000. So when you're trying to do stuff like this, make big jumps initially, and then it's easy to come back making smaller and smaller jumps. Okay, so 1,000 definitely shows me what's going on here, but notice we're really losing some detail, or at least in our red line. Like it's sort of hard to see compared to this. So I can get rid of pretty much everything above 700, maybe even above 650. So I'm going to take this down to 650. And there we go. That seems pretty good. The bottom is a little cut off. I'm actually going to, because this is so big, I'm going to make this go down to -50. Yeah, that works a little bit better for me. And now what I can do, all right. So that's how I've constructed this. I'll explain it here in a second, but I want to get it into the Miro board for that. So share the Miro board again. While I'm doing all of this, I'm going to check the email and the form for any question submissions. Don't want to get too focused on this spiel and miss people's questions. That's what we're here for, ultimately. Okay, email, I don't see anything. Form still says 0. Okay, cool. So back to this. Let me get this graph into the Miro board. And one of the things I like about the Miro board, though, is I can just screenshot, boom, paste in. Actually, here, I'm going to... Those lines are a little hard to see. I'm going to take the extra... There we go. Boom. Make the lines a little thicker. I didn't show you how I did that. It's okay. There'll be lots of time to talk about using Desmos. Oh, that's nicer. You can see those lines. They're not nearly as thin. Okay, so there's that. I also want to grab the equations for us. Okay. Boom. Now we can stick those together and we can zoom in. Okay. So what are we talking about here? What are we even looking at? Make it small enough and get my head out of the way. Eventually I'll also be able to adjust my little inset, and that'll be nice. Can I? No. Okay. I just want to see if there were like maybe settings that I wasn't aware of. And no. I don't think I can like drag this, can I? No, this is just a feed of my, okay. All right, so what are we looking at here? So this is our optimization problem, right? So so goal, optimize the enclosed area, the product L times W. So you can see L times W, that's the green. So the Y value represents the product of these. For the green one, that's what the y-axis represents. It represents the amount of area that's enclosed. And so you can see, and so what does the x-axis represent? So for both graphs, the x-axis represents the L value, the length, right? And so that's kind of, I made x equal to L because it's length and they're both horizontal. I figured that was a little bit more intuitive. It doesn't matter which one you make x. And because W and L are so connected, if we know what L is, or x, we automatically know what W is. If we know L is 10, then W has to be 40 because they have to add up to 50. And so the red line, so the green curve, the y value is the area enclosed, how much area is enclosed, how many square feet are enclosed by this 100 feet of fence. And the y value, or the x value, is what the length value would be for that enclosed area. So if we make the length 10, so the width would have to be 40. So we go up here, 10, and oh, 10, and here's 40 for this, right? So there's 40, there's 100. So it's really small there. It's really close to 50. But also at 10, the enclosed area is 400. And that makes sense because 10 times 40 is 400, right? And so this picture of these two things, this is our constraint problem. The red line is, so for the red line, the y-axis represents the width, the corresponding width. So every point on this line, the x and y add up to 50. So if we want to use all 100 feet of fence and no extra, we can only use numbers that are on this line. But that's every number between 0 and 50 for either L or W, right? So that said, the optimization here, once you graph it, is very straightforward. The highest point of the curve of the thing we're trying to optimize is the largest point. And we go down here and we say, okay, well, where is that at? That is right at 25. That's right in the middle. Right, we can see it's directly between here and here, and there's 5 here. So this is 20, this is 30, 22, 24, 26, right in the middle. And in fact, if we go back over to Desmos, I guess I could have just done this. If I click on this, boom, it gives me the top. 25, that's X, which is L. And when on this graph, when L is 25, W is 25. So the top there, the maximum area, 625, and then we can see as we drag along and make the length bigger, 605, 530. You can see the y value is going down, and same thing the other direction. As we make the length smaller and therefore the width bigger, the total area, 545, 508, goes down. The largest area you could possibly get to with two numbers that add up to 50, because when you double them, they need to add up to 100, is 625 square feet, if we're talking about feet. Now, granted, there might be a lot of reasons you don't want a perfectly square enclosure. Maybe one dimension it needs, for whatever reason, to be exactly 40 feet. So your decision's made up. You have to do 60-40, and there's not really any, at least you're not optimizing area there. You're optimizing for other things, right? And so if we go back to this, so this is, all things being equal, length and width are equivalent to each other. But there's all sorts of variations on problems like this. So for instance, I think for this maybe I'll just type it just so it's more legible. That's pretty big. Okay. So let's change it to just black for right now. Okay, so a variation on this. Oh, with 100 feet of fence, you need to enclose. There we go. Anyway. Oh, actually. Ooh, let's make a change to this. So okay, yeah. You need to enclose 500 square feet next to a barn. A barn wall that is 75 feet long. What is the minimum amount of fence necessary if one side of the enclosure can be the barn wall? Right. That's why I included the detail about the barn wall. I thought that would be obvious, and then I said that I decided I would express it explicitly and say no. You can use the barn wall. So this is a slightly different problem, right? I mean, not a slightly different problem. Our goal, what we're trying to optimize here, is different. So we can ask ourselves, what are we trying to optimize? Right, that's the first place to start. What are we trying to optimize? In this case, we don't want as much area as possible. We want exactly 500 feet for whatever reason, right? And this is where problems like this get a little contrived. Why couldn't it be 501? Why couldn't it be 498? Now, that minimum number, maybe they're trying to meet, the organic label that things get in the USDA certified, all those sort of things. In addition to paying for those certifications, the producers also have to meet certain criteria. Sometimes all they have to do is pay for it, but sometimes they have to meet certain criteria, like that their chickens had access to a certain amount of free space per chicken, right? And so this person has, based on the number of chickens they have, they've calculated that they need 500 square feet for this enclosure, for their enclosure to meet the standards. So boom, we have some sort of justification. This is not completely contrived. So what are we trying to optimize here? Since we're not trying to optimize the area, we're trying to, what is the minimum amount of fence? And now, this is a different sort of optimization, but it's still optimization. We're trying to find the optimal thing. In this case, we'd like to use the least amount of fence because it'll be the cheapest, or leave us with more fence to use for other projects, or whatever. So we are trying to minimize fencing, right? And so this situation that we're in, right, we have, this is our barn. I'm going to scale up our barn. There we go. There's our barn. And then we need to make an enclosure that again has a length and has a width and needs to be 500 square feet, right? So we need to minimize the fencing. Now, here's where this changes, right? Our amount of fence, right? So minimize fencing. I'm going to call that capital F. So our capital F, our amount of fencing, is going to equal 2 times the length of this plus 1W. So notice now that the thing we're trying to optimize is not symmetrical. Before it was 2L, 2W, so you can just divide them both in half. Now, the L is weighted more heavily. There is more, well, not necessarily. If the length is less than half the width, then even 2L is going to be less than W, but we have to take that into account. Other questions that are kind of like this that they talk about like, oh, one side of the fence is going to be really expensive because that's like the side of the fence that's facing the road. So they're using a really nice thing, but then the rest of the fence is going to be like cheaper, right? And so you have this single side that's more expensive. So what you're trying to optimize that in a situation like that would be cost. You're trying to minimize cost. Here, we're just trying to minimize actual material use, but that's probably to minimize cost. All right, so that's the thing we're trying to minimize. We want to, actually, you know what? I introduced this variable, but we don't have to do that. Instead, we'll just say the minimum of this. We want to know what the minimum of 2L plus W is. Anytime we have an optimization, we also have a constraint. So we want to ask ourselves, boom, boom, boom. What are the constraints? Now, oftentimes in math class, especially if you're in algebra 2, even all the way up to like calculus, you're probably only going to have one constraint, because the complication compounds really quickly as you add more constraints, and so we're really probably only going to have you focus on problems with one constraint. But you can also approach constraints in sort of we'll deal with this constraint, we'll optimize for this constraint first. Okay, now that we've optimized for that, and we're working from this sort of optimal basis, now let's consider this other constraint. How do we adjust from where we are to now optimize for that constraint, right? And I mean, that's a single approach. There's so many different ways to do this. That's why I'm saying the complication compounds. By the way, so in our case, what are we actually constrained by? It's the area we want to enclose. Now, I don't really know why it would be a problem to enclose a bigger area more than 500 feet, but I think the idea here is, well, if you're enclosing more than 500 feet, you're using more fence than you need to. This person needs 500 square feet. So if you enclose 600 square feet, you could definitely have used less fence, right? So I think that sort of plays into the constraint. So our constraint is this area. We know that L times W has to equal 50. And now look at how different this is, or how this is different from the previous one. In the previous one, the thing we were trying to optimize was the product. And our constraint was a sum. Now our constraint is the product of, this should say 500. 500. There we go. And the thing we're trying to optimize is the addition, right? And so if we, let me, so because our constraint is this multiplication, our relationship here, right? If we were to solve for W by dividing by L, we could express this constraint as 500 over L. over L. There you go. That's how we'll express it in Desmos, because it likes that notation a little better. And then here we will do 2L plus OW. There we go. All right, now, so I will share this now. So instead of throwing this in the Miro board again, I will still throw it in the Miro board, I guess. Mostly, for going back to. All right. So what are we looking at here? Similar thing. The red here is our is that constraint. There's that 500 square feet. Divide it by whatever the length is, and we're letting our x-axis represent the length of the enclosure, right? 10, 20, 30, 40 feet. So if we know what the length is, then to figure out the width, we take the total enclosed area, 500, divided by that length, and that has to be the width, right? So this is our constraint, which makes this our optimization equation, the thing that and now remember, we want the minimum of this. Notice, so our constraint equation and our optimization equation sort of follow a similar path here. We could talk about what that means, but that's not what I'm focused on right now. Because I have this equation selected, the green equation, notice it puts a dot right here. That is, in fact, the bottom of this. A graph like this can be a little hard to tell where exactly the bottom is, but here it is. So the numbers are messier than the last problem because I pulled the 500, out of the air. This could probably work out more nicely if I made this a better a number that works better with this problem. But the real world is messy, right? So what this tells us is L, so X right now is 15.8, almost 16. So when the length is almost 16 feet, which 500, so right at the same point, 15.8 right there, then the 15.8, then on the red curve, we can see that W would have to be around 31. 31, a little more than 31 and a half. So when that's true, when the length is not quite 16 and the width is a little bit more than 31 and a half, then the total amount of fence you would need, because that's what this represents, is 63 and a quarter. That's almost 63.25. 63 and a quarter total feet will allow you to enclose 500 square feet so long as you use the barn as the width. So notice the width here is the bigger number, right? Because that makes sense that you would want to use the barn as the longer side, and that way you only have one long side instead of two long sides, right? And that way, in the construction of this. So yeah, there's all sorts of ways you can change up even a simple optimization problem like this, an enclosure problem, but then there's all sorts of all sorts of optimization has to do with saving money or potentially maximizing money if you're trying to maximize profits and stuff like that. But also we often want to minimize materials used. We often want to maximize, strength and stability of structures and things we build. So optimization is all over the place. And really, I'm going to say any optimization problem can be worked with and processed to the point where you can graph it and just find the lowest or highest point on a graph. For the most part, right? There are some much more complicated situations where it's still analogous to this, but you're just working in multiple dimensions. But yeah, if you can and so notice we worked with this so that we could express it this way, right? the W times L equals 500, we rewrote it this way. And we even had to come up with those equations, right? Using the tool saying L equals X, like all of that is processing this problem into something where we can just say, oh, it's the bottom of this graph. But that's the whole point, right? And that is the power of math, is it allows us to take complicated things like this, right? Like, imagine trying to solve this problem without Desmos, without, just talking about the idea of wanting to enclose 500 square feet, having this part, like and we could totally sit down on paper, and there's totally other ways to do this besides graphing it. I just think graphing, especially on a visual medium like this, right, is particularly interesting. But there's algebraic ways to deal with this as well. And that's actually something, not algebraic ways, there are calculus ways to deal with this. This is something that calculus is really, really good at, is dealing with optimization. That could be, heck, maybe on Sunday that I'll pick up here and say, hey, let's continue talking about optimization. Now let's talk about it from a calculus perspective. How can we, so we looked at the graphs, but how can we find these same things without a graph? And that when you're dealing with more complicated multidimensional types of optimizations and constraints, the graphs can become less helpful, right? It can be harder to see visually the important bits. So understanding how to find those places via the math itself becomes more crucial. But it's all still related. The graphs are just showing us visually something we can also see mathematically. Cool. This is I knew I wanted to talk about something related to this, but this is not exactly where I expected to go. So this was fun. We'll get ready for the Sunday stream. Sunday. Sunday is going to be 16, 17, 18, 19th. So yeah, I have jury duty tomorrow. So I'm just preemptively not streaming. There is No Kings 2 on Saturday. I hope you're going to. I'm treating it essentially like a 4th of July type of thing. It is a very American thing to gather in the streets and say we won't be ruled. That just strikes me as one of the most American things there is. It strikes me as what, 4th of July once upon a time kind of was and felt like for me. So, and it's going to be a family friendly, it's just, Eugene, that's where I'm at, I imagine most of the people watching this are probably going to be local. It's just going to be people in Eugene coming out to just reaffirm to each other that our democracy is important to us, and that we won't tolerate steps that move to shake that democracy in any way whatsoever. And I mean, I don't need to be specific or anything. That's just true regardless of what's happening, regardless of who's in power. Yeah. So I hope you're out there. I think it'll be good. I think it's like 10 to 1 is what it's scheduled, and it's going to be at like that courthouse, kind of near the like river or the Coburg like turnpike thing. Anyway, I think that's what I've got, I guess. I'll get the website ready for Sunday. Oh, I need to get the website ready for tomorrow. I completely forgot. I need to get the website ready for tomorrow for the fact that I won't just like some sort of messaging about there not being a stream. Okay. Okay, we're deleting that stream. I won't put in the Sunday stream stuff. What I want to do instead is, so where the stream would normally appear, right? It's like a video thing. I just want to put the thumbnail that I would put on a non-stream. So let me see. What's happening? Oh, there it is. Okay. Awesome. Okay, that's exactly what I want. I already have a graphic for this. So what I want to do, okay, I'm in the visual builder. I want to, what are you all seeing right now? Sorry. Okay. So what is this if I edit this? Okay, I will be right back. Okay, back. Video. Oh, really? Ooh. Can I hold on a sec? I think I don't know what this is gonna do. I might be able to. No, I'm gonna have to go in here anyway. Okay. I got rid of it. Okay, hold on. Nice. Okay. Excellent. This is okay. This is actually working really, really well. I'm so pleased. I'm so pleased. Let's just chugging. There we go. Oh, is it doing something? It's trying to do something. Haha. Nice. Nice. Okay, so during the Thursday stream, this will pop up with a little graphic that says there's no stream. If people try to play it, it will just try to connect to Sunday's stream and tells them 3 days. That's excellent. So, I think that's everything, y'all. I think that is a homework help stream. Not a terrible one, as these things go. I hope you all have a great night. I will be back Sunday. Please submit your questions. The thing is, if you submit questions in between sessions, I might just respond to them, and then I'll still talk about them on stream, especially right now while it's slow. But like I might be able to help you out before the Sunday stream if you need some help. Honestly, if stuff comes in Thursday while I'm just waiting around at the courthouse to see if I'm needed as a juror, I would probably have an opportunity to address some of it. So even though there won't be a stream, please submit questions. And at the very least, I will get to those questions on Sunday, and we'll have a chill Sunday stream. Thank you all so much. Have a great rest of your week. See you later.